All right, so in this paper, I'll be going over the screencast ultraconservative online algorithms for multi-class problems. And I guess I'll talk about what this ultraconservative is. But basically, this is a multi-class perceptron. And here are the authors. I believe it's quite a simple but good idea. So I believe this is an important paper. So as I said, the main idea is that it uses multiple vectors for multiple classes. So here there's obviously 3 classes. And in the old algorithm, we might just have one vector like that. And then if you take a point here, then this vector dotted with that would be positive, and we say, oh, so this should be the purple class, right? And right here, this vector dotted with that would be negative, and so we say, oh, this should be the green class, right? So that's how we divide between 2 classes with a single vector. So that's the 2-class perceptron, just to review. Now, obviously, with a single vector, you can't distinguish between more than 2. And let's get rid of that. And so the idea then is to have one vector for each class. And then when you get a new point, you say, okay, let's take this vector dotted with that, this vector dotted with that, this vector dotted with that, and we see which one wins, which one gives the biggest dot product. And if this one gives the biggest dot product, then everything's fine, no update. If, say, this one gives the biggest dot product, so we're predicting it blue, but we know the point in our training set is actually, I guess, purple here, then what we would do is we'd say, okay, well, we better make this vector smaller, and we'll make this vector bigger, well, no, sorry, let's make this vector more in that direction, and this vector less in that direction. And so we'll add a component like that onto this one to make it more in that direction, and we'll subtract this component. So we'll end up, this vector will become that, and this vector will become that vector. Hopefully that all makes sense, that update there. Just to make sure it's clear. So these would be the new vectors in red after the update, where we predicted blue for that one when it's actually purple. All right. So that's the idea. Use multiple vectors. Now, there's also balanced updates. So in this example, I increased the component of this vector in that. Basically, I added this vector to that vector, and I subtracted this vector from that vector, right? So that's balanced in that I've added a certain amount in this direction to one of them, and a certain amount in the opposite direction to the other. And yeah, balanced is good. So what we could do is imagine we're in lots of dimensions and that there's lots of different classes. Possibly more than one class will beat the correct class, right? And so then maybe we should decrease all of them. But what we don't want to do is don't increase the correct one by, maybe let's call this point P here. So we don't want to increase the correct one by P and decrease all of the incorrect ones by P. We don't want to do that because, say, we could be adding this onto that, and we could be adding that onto that, and then overall, you're just going to make the size of your vectors grow because maybe you're decreasing. On an extreme case, you could have 10 or 100 incorrect ones, and so you're increasing all 100 of those, which they then get out of balance because the balance between the size of the different vectors is important for which ones wins. So they get out of balance with all the ones that weren't updated, and so then you have to update those, and you just keep having to update different ones. So we want it to be balanced. So what we can do is say both of these. Obviously this one wouldn't be picked for predicting that, but just for the sake of argument, maybe in multiple dimensions, which we can't see, this one would actually predict that ahead of that. So if we want to update several, we can say, okay, I'll just update this by half and that by half of the negative of this vector, right? So therefore, this vector that we're adding onto here, and this vector, all of them add up to 0. 0 net change. So basically, all the vectors, so for all the different classes, sum to 0. I'll save the perceptron vectors. I'm making up that term for all the different classes. Now, I want to explain what this error set is here. The error set is basically, i.e., any vector that beat the correct vector, right? Corresponding to the correct class. Cool. And this this leads us to the definition of ultraconservative. Only the correct vector and the vectors in the error set are outdated. So just erase that. So things are how they look here. Maybe this one beats that one when we're predicting this. So there's only this one vector in the error set. This one didn't beat that one, so this vector isn't in the error set, right? And so we're only going to update this vector and this vector because this was the correct, corresponds to the correct class. All right, so that's ultraconservative, and we've gone over how it's multi-class. Obviously, the perceptron is an online algorithm. So that's the main idea, and we'll be going over details and proofs and optimization of the algorithm, making it extra good, and different variations in future screencasts. Thanks for watching.